Hello everyone, welcome back to Deviations. So in today's video we are beginning trigonometric substitution. This was something that I've been learning to quite a lot, and to be honest it's quite a doozy of an integration technique, but you'll see why. We're going to be actually dealing with some pretty crazy functions here, and we're somehow going to be connecting radical functions to trigonometry, which is something that I just think is so cool. So yeah, buckle up because this is going to be quite a ride in our calculus journey. So without further ado, let's start talking about the cases for trigonometric substitution. We're going to put them all on the table right now. So we deal with 3 trigonometric functions. You can deal with the other ones, but just why? We can deal with these ones a lot better. So we're going to be talking about sine, tangent, and secant. We're only going to be doing one example in this video, but don't worry, there's more to come later. So we'll get started by talking about the cases right now. So the first case says that there is the expression where we have the square root of a squared minus x squared in somewhere in our integrand. So what we do is we take a triangle. This is going to be an okay drawing of a triangle. Okay, so there's our triangle. So this guy here is showing this is showing some sort of Pythagorean relationship, right? So we've got a squared minus x squared. Now what does this mean? So a squared minus x squared is telling me that a squared is the length of my hypotenuse because we're subtracting something from it. Well, no, not a squared there. Then we're going to have an angle of theta here. And we want our x value to be equal to a sine theta. So then we're going to have x equals a sine theta with the domain of negative pi over 2 comma pi over 2. This isn't terribly important until we start talking about definite integrals. But let's cover this. So if we have a sine theta, then that means that, our sine theta, by definition, or by our SOHCAHTOA definition, we have opposite over hypotenuse. So that means that this is going to be x. And then this here is going to be x squared minus a squared. So there, our substitution here makes perfect sense. Then we also have the time where there exists the expression the square root of a squared plus x squared. So in that case, we're dealing with theta there, and we've got here our Pythagorean guy here, because we're adding these sides, so that means that we're going to have a squared plus x squared. And in this case, we're dealing with an instance where we want to find that x equals a tangent of theta. So theta is going to be the inverse tangent of x over a. So x over a, we have tangent as being opposite over adjacent. So then we're going to have x here and a here. And this is with the domain of negative pi over 2 to pi over 2. Again, this is not important currently. Then we have the final instance where we have x squared minus a squared. So in this case, we have x as our hypotenuse because we're subtracting a squared. And we're trying to find that x is going to be equal to the secant. So the secant, that means that the inverse secant or theta is going to be equal to the inverse secant of x over a. But of course, in this case, we have that the secant is equal to the hypotenuse over the adjacent side. So that's going to give us that the adjacent side is a, and this missing side is x squared minus a squared. Right. So now I think we're ready to do an example. We've got our 3 cases. We're only going to be looking at the sine one now. So, let's look at this example. I want us to integrate the square root of 4 minus x squared dx. So immediately we see the 4 minus x squared. So this is pretty evident that we're dealing with a sine substitution. Whenever you have a constant minus your variable squared, then you're going to do a sine trig sub. And we set x equal to the square root of a sine theta. Square root of a, in this case, is 2. So x is equal to 2 sine theta. Now we also need to find our dx, because we do have a dx in here too. We need to make sure that we get rid of all of our x terms, so we can change them all to thetas. So dx is equal to 2 cosine theta d theta. Now we're going to see why trig sub is so cool. Once we plug all these in, we're going to be able to solve this integral no problem. So we're going to get the integral of the square root of 4 minus 4 sine squared of theta, 2 cosine theta d theta. Now this is going to look like a mess, but it's going to substitute, or it's going to simplify real nice. We're going to pull the 2 out, or we're going to pull the square root of 4 out from both of these guys and put it outside the square root. So that gives us the integral of 2 times the square root of 1 minus sine squared theta, 2 cosine theta d theta. Now you probably already see where this is going, because this gives us a Pythagorean identity. So this gives us 4 times the integral of the square root of cosine squared theta times cosine theta d theta. Take the square root, multiply that by cosine theta, and you're looking at 4 times the integral of cosine squared theta d theta. Now we know how to do this through reduction. We're going to pull out a 1/2 here and just make that 2 there. So that gives us the 2 times the integral of 1 plus cosine 2 theta d theta. This is something that we can integrate real fine. And this is going to give us 2 theta plus sine of 2 theta. Okay, so now we have found an answer, but we are not done yet. And this is what the kicker is for trig sub, because now we need to go to our triangle. So we're going to draw. I always recommend that you draw a triangle in these problems. I know you think it's silly, like from geometry, but no, we are going to be using a lot of triangles in calculus, especially in trig sub. So now we need to find theta. So if I have the expression, we're gonna need a lot of room. So if I have the expression x equals 2 sine theta, then x over 2 equals sine theta. So then theta equals the inverse sine of x over 2. So that's how we derived that there. So now, we need to look at ratios. So x over 2. So if sine of theta equals x over 2, and we use that SOHCAHTOA definition. So we have the opposite over the hypotenuse. So that means that that is going to be equal to x, and that here is going to be equal to 2. So that means that this missing side is equal to 4 minus x squared. Right? So now this is important. I always recommend labeling your sides here for your triangle, because now with this integram we're going to need to find what theta is equal to and what sine of 2 theta is equal to even. Believe me, that's a mess. So yeah, we're going to dive into that mess right now. So we've got to find 2 theta. So 2 theta, that's pretty easy. That's just equal to 2 inverse sine of x over 2. Right? Now that's pretty easy to understand. Now we need to look at the hard part. So we need to find sine 2 theta. So in general, sine of 2 theta, if you remember from trig, is equal to 2 sine theta cosine theta. So now we need to find our cosine theta value. Now what is cosine? We know what sine theta is we need to find what sine theta is equal to actually. So sine theta is equal to the opposite over the hypotenuse. So that's equal to x over 2. So sine theta equals x over 2. Now we need to find cosine theta. So cosine theta is the adjacent over the hypotenuse. So that's the square root of 4 minus x squared over 2. Okay, so now we've got to multiply this. So this is going to be equal to 2 times x over 2 times the square root of 4 minus x squared over 2. Right? So those two cancel. this gives us here x over 2 times the square root of 4 minus x squared. So now we've found the sine of 2 theta. So now we can plug that back into our integrand, and this is going to give us our final answer. Finally, we get 2 times the sine inverse of x over 2 plus x over 2 times the square root of 4 minus x squared plus c. Okay, now, I hope you understand now why I've hyped trig sub up to be such a big deal, because look at all this freaking work we've just needed to do. We've needed to do this, we've needed to do like a substitution, which is already quite a bit of work. Then we've needed to do all of this algebra with the trigonometry. Then we've needed to dive into all of these identities here and build a triangle to find our integral. And what some people end up doing is they're kind of lazy, and they just like put in theta there and put in that thing. You don't want nested trig functions, so please try to find your